And for those people who told us in time, we have set you up accounts, and you should have some emails about your username, your temporary username on the system, and how to pick up your temporary password. If you just turned up on spec and you're just interested to see what the session's like and you haven't registered, so you're not going to be able to do the practical, it might be wise to rearrange the seating so you're sitting next to somebody who is registered, so that you can at least crib off their screen and pair up. Laura. So the question is, can you do the practical on a different computer? And the answer is yes, but we can't support it. So it may or may not work. If it doesn't work, that's your problem and not ours.
Stop.
Question, out of interest, how domain, like how specific is this to the Cambridge HPC? And if I run it on our HPC, which has GPUs, would it in principle still work?
If you've got NVIDIA GPUs, it'll work. If you've got Intel GPUs, it'll work. If you've got AMD GPUs, who knows? Ask AMD. It should work, but in theory it works, yeah. It's platform agnostic. If you haven't got GPUs, it still works. Yes, it's fine. Maybe we'll be using A100s now.
Thank you for all the questions. I'm glad that everybody is keen. What we'll do is we'll get on to the practical exercises once we've learned a little bit about OpenMP and OpenMP target offload. So first we're going to do some, Arjen here, I'll introduce, is going to do some lecturing. By the end of that, theoretically, you will have all the information you need to know to do the exercises. And then the exciting bit is to find out whether or not you do need, you have learned some OpenMP. So we'll have a coffee break. We will make sure that we have the coffee break at scheduled time. So wherever we're at with lecturing or exercises, we will break coffee at 3:30. No, it's 3. From 3 till 3:30.
Yeah.
And then those of you going to the dinner, we'll be leaving here at 5:15. So this session wraps up at 5. I think we'll all be exhausted by then. And then there'll be buses to take us to Manley Hall. So thank you. Welcome along to this afternoon session on Introduction to OpenMP for GPUs. If you haven't met me before, my name is Chris Edsall. I'm one of the co-directors of the Institute of Computing for Climate Science. Unlike Emily and Colm, who are based in academic departments in the university, Arjen and myself are based in University Information Services. So that's the third department that hosts people from ICCS. That's where all the RSEs sit. So if you've met all the RSEs, they're in the same department as me and Arjen. Where this is a little bit different, I've got lots of hats, and Arjen and I share the Cambridge Open Zeta scale hat. I should be using the microphone. Yes. So zetascale relates to zettaflop and also zettabyte. It's 10 to the 10 to the 18? No, 10 to the 21. 10 to the 21 flops. It's the next power of 1,000 times up from exascale. We have one exascale supercomputer in the world, Frontier, at 1.1 exaflops. We've now got Aurora at 1.12, so we've got 2. Hopefully by the end of the year, we'll have El Capitan, and we'll have at least 3 exascale machines. The Cambridge Open Zetascale Lab is focused on what do we need to make a supercomputer 1,000 times bigger than that. And we look at all sorts of things like energy efficiency, networking, storage, and relevant to today, we look at programming models for large HPC systems. And for energy efficiency reasons, they're probably not in the future going to be CPU only. So you are going to have to program heterogeneous machines of CPUs plus GPUs somehow. And this is one option. Right, so I think at this point I'll hand over to Arjen, who's the senior research software engineer in the Zettascale lab, and he'll teach you some OpenMP.
Thank you, Chris. Okay, right. So thanks. Like Chris said, my name is Arjen. I'm a senior RC in the OpenZScale lab. So this slide is saying this talk is by myself and Chris. We've also got Tom in the room who can help out with the exercises. I think Miriam will be able to help out with some system work as well. It's over there. Sure, maybe, perhaps, if you feel like it. Super. So as Chris said, we have to, do a little bit of self-promotion. So I'm part of Zettascale lab. Chris did the introduction. Here's the text version, so you can read it back when you're down to the slides. So, right, goal for today is to get you going with OpenMP offloading. I'll get to what that means in a bit. So it's going to be about an hour of me waffling to you. And by the way, if you have questions, just interrupt. And then about 2 hours of practical exercises. So yeah, first an hour of taking a lot of information and then 2 hours of actually learning. And one thing I should say, so OpenMP is quite a big specification and it's going to take a lot more than a couple of hours to actually learn everything. So going to focus on a small subset of OpenMP, which is like we call loop parallelism. As really, the idea is to get you familiar with, how do I use OpenMP in my code? How can I get it running? And I think, this is something that I might want to use in the future. There's, a lot of extra material to get familiar with later. First, so first question maybe to ask is why would we want to go parallel? Like Chris said, we've got these big exascale machines coming in, got hundreds of thousands of CPU cores, all these GPUs. But even if you're just working on one machine, like your desktop or one server, if you go back about 20 plus years, most processors were just, you've got a CPU, it's got a core, does some calculations, and if your CPU is fast enough, just you buy a fast one, or maybe you wait till next year. And maybe if you did work on a supercomputer, you might go parallel, connecting a bunch of servers together and distributing your work over that. If you go to, I believe about the mid-2000s, this whole shtick of, oh, my computer is fast enough, I'll just buy a faster one. It kind of stopped working. We reached the limit of frequency scaling and mostly power scaling for a single core. So, companies like Intel and AMD start to put more CPU cores in a machine. And that kept increasing. And then from about mid-2010s, there's a company called NVIDIA, who's doing work with GPUs, now rendering for video games. And they generalized the architecture and they thought, hey, this is basically an algebra machine. Can we just use this for general purpose computation? And then fast forward another 15 years and we've got AI and now we're all here. So if we draw it out, this is the good old days where we just had a CPU and we had some memory. That's all we had to worry about. Then again, a bit later, we've got still the same memory, but we've got a few more cores we have to deal with. And you have to sort of think, how can I use this efficiently? Do I just want to run a bunch of programs, or do we want to have these cores work together? And now we're in this situation where I've got a CPU with a whole bunch of cores I have to keep happy. And I've got this whole extra device attached to it with its own memory, and oh God, how am I going to deal with this? So yeah, and how I'm going to deal with it, there are many ways to deal with it. And a hopefully relatively easy access method is using OpenMP. So many programming languages, and I'm real thinking in more the simulation style languages like C, C++, or Fortran, but also languages like Python mostly, they're still inherently serial in the nature. If you just write your code, it'll run on one core, that's it. And OpenMP was introduced as a way to make parallel programming accessible, most crucially without having to learn a fundamentally new way of writing your code, a new way of dealing with your hardware. and also with minimal changes to existing serial code. So if you already have a code, it's working fine. You just want to make use of, these extra resources in your machine. You don't have to completely rewrite everything. So yeah, again, first release was around the mid-90s, I think, for parallelism on the CPU and support for GPUs, which were really interesting these days. Really got added again around 2015. Right. So that's OpenMP parallelism in a nutshell, in the history at least. So OpenMP, what's special about OpenMP is it's a directive-based programming model. So instead of it actually being a programming language, it uses annotation in your source code to instruct your code compiler to generate parallel code. And it's really only for C, C++, and Fortran, so apologies to any Pythonistas in the room. But if you're not too familiar with these languages, when it comes to exercise, we're not actually be writing any code, we'll be writing directives. So as long as you're comfortable with reading, this style of code, you should be fine. Today's focus, or at least our final aim, is to get you going with offloading, so generating code that runs on your GPU. But we have to cover some CPU essentials first, just to get you going. Yes, you can.
Just to understand where MP fits into things out there, right? Mm-hmm. What is the equivalent of OpenMP in other languages?
That's a good question. Is there a real equivalent in other languages?
So
it's yeah.
For the recording, the question was, what is the equivalent to OpenMP in other languages? And the one way of addressing that question is to say it's not, OpenMP isn't a language, it's an addition to these three languages that Arjen's mentioned, C, C++, and Fortran. In theory, you could imagine, putting OpenMP directives into Julia or Python, but that's not how it's done. In Python, there's multiprocessing as a package, which allows you to make use of all of the all of the cores on one server. There's Dask, Dask distributed. There are a number of library-based solutions in Python and also in other languages. So Rust, I think you might use Rayon. So yes, there are for other languages there are other approaches. I do know somebody who's parallelized a large Python program using OpenMP, but they had to go through a separate step using a thing called Cython, which basically is a source-to-source translation tool for Python, and it produces, you annotate your Python with C types, and then it spits out some C code, and then you can put the OpenMP directives in that. But yeah, I think if you have C, C++, or Fortran, this is an approach to go down. If you have another language, use that language's native approach, or that language's libraries, or use that language to call into C, C++, or Python, use the foreign function interface. Yes?
How does OpenMP relate to MPI?
The question is, it's a good question. How does OpenMP relate to MPI? And we both stumbled on the fact that there's an MPI implementation called OpenMPI, which is super confusing. The simple way to think about it is MPI single node. God, it's confusing. OpenMP single node, MPI multiple nodes. So OpenMP is.
I blame OpenMPI or who were first?
Yeah.
Whoever was second.
OpenMP shared memory, MPI distributed memory.
So they actually you can work together very well. So you can MPI is for scaling out. Like if you want to run on multiple machines, you would use MPI to it's path management between the machines and coordinate your parallel computation. Like Chris said, OpenMP is very much meant to work within a single node. It doesn't really have any capabilities, or it's not designed to go outside of that scale. So if you want to parallelize over a lot of compute units within a machine and go outside, you tend to combine it. So it's kind of hybrid OpenMP MPI, which a lot of people talk about.
So don't know if you're going to talk about this, but since you're focusing on the GPU,
Yeah.
what about OpenACC? Like,
OpenACC is basically it's a competing standard to OpenMP. They can be quite similar. So if you're familiar with OpenACC, you're not going to see a lot of surprises today. It's directive based. I think OpenACC is a more recent standard, and it's designed from the ground up, really, with GPUs or accelerators in mind. Not necessarily. The big difference is vendor support. So OpenACC is very heavily promoted or supported and promoted by NVIDIA. So if you know that if you're exclusively going to work on NVIDIA hardware, sure, go ahead and use OpenACC. But if you want to go on run on Intel GPUs or AMD GPUs, OpenACC might not be as well supported.
I'm going to add a boring political slant to that answer as well. There's an extra thing, which is who's in control of the standard, who's in control of the programming language model. So if you have a standards-based programming language or programming language model, then there'll be some neutral party that defines it. So say in the case of C++ and Fortran, it's the International Standards Organization. So that's ISO C++, ISO Fortran. In the case of OpenMP, it's an organization called the OpenMP ARB, the Architecture Review Board, which is composed of, you can go onto their website, there's about 30 vendors and user organizations. Who's standardizing OpenACC? So if you're going to choose, I mean, you can be pragmatic, right? If you're writing some code to throw away and it only needs to last for the next 3 months to get your paper out or whatever, then choose whatever programming language and model you like and don't care about the sustainability of it. But if you do care about the sustainability of it, if you're thinking about, say some of the software in the US exascale computing program has been around for 30 years, if you're thinking about software on that lifetime, you want to be assured that your programming model is going to be around, or your language is going to be around for that length of time. And you really, in that case, want it to be multi-vendor and sort of vendor agnostic. So I personally think the standards organization is important.
Yeah, so I'll say, I'm not going to make any statements about which model is better. I have opinions about it. I'm going to keep them to myself. I could say, when it comes to support, OpenMP is at the moment much more widely supported than OpenACC is. All right. So, So I mentioned, OpenMP is a directive-based language. Well, a slide there. Yes, directive-based parallel framework, and again, as I said, it extends the language into C or Fortran transparently. Your code itself is not necessarily affected by a directive unless you explicitly tell the compiler to do it. So you could write a bunch of OpenMP directives, and if you want to test your code without OpenMP, you just switch flag off in your compiler, and it works as it used to without any OpenMP. So as an example code I'll be using throughout these slides is SAXP. So SAXP is a single precision AX plus Y, so it's a vector addition and scalar multiplication. It's quite a simple loop. We just iterate over 1 to n, and we calculate AX plus Y and store it back in Y. Here in Fortran syntax, because I like Fortran. So if we take this loop, if we want to parallelize this with OpenMP, we add these like so. So in Fortran, we say exclamation mark OMP, this is the OMP sentinel, and then parallel do, keyword to take this do loop and parallelize it over, in this case, my threads on the CPU. And we have to tell it to where this loop ends. And that's really all it takes. And for people who prefer C, the syntax is slightly different. Instead of this exclamation mark $sign, we say pragma OMP and parallel 4. Because C has 4 loops, not 2 loops. And in this case, we don't have to have an AND pragma because in C, the directive bind to, oh, that hurt, curly braces. Right. Right. And so this is actually a compound directive. So we're doing 2 things in this loop. We're saying OMP parallel, which is the key to your compiler. Say, okay, at this point, I want to create a parallel region. And when we're still on the CPU here, this tells, okay, spawn a bunch of threads. And so a thread is a lightweight process. And run one on each of my cores. And all these threads will be doing the exact same thing. They're running through the exact same code as it's written within that parallel region. And then the OMP do directive is the instruction that tells, okay, what's following this do key, which is going to be a loop. I want you to take the work that's doing and distribute it over all the threads I've just spawned. And so, cool, that works. One thing that is important to keep in mind is, you're working with data here and your threads might be accessing, you have to think about what data are all these threads accessing. And so OpenMP has a concept called data sharing. So by default, any variable or a scalar or an array that's declared before you enter parallel region is shared between the threads. It means they're all accessing the same physical elements in memory. If you declare a variable within a parallel region, that means it's private. It means that every thread gets its own copy of that variable. And the other threads can't touch it. So these are the defaults, but that might not necessarily be the way you want to access our data. So we can use data sharing clauses to specify how these variables should be shared, or if they should be shared at all. So they can be shared, they can be private, or they can be first private. The difference between private and first private is if you have a variable already declared before you enter a parallel region, and you say, okay, this element is private, then everyone's going to get a copy, but it's not going to be properly initialized. So you can't rely on what the value is going to be. If it's first private, you tell, okay, create a private copy for every thread, and it would be the same value as it was before you entered the parallel region. So it's really important to keep this in mind, because if you've got your data sharing wrong, it's going to lead to very painful debug problems, such as race conditions, which means like if you've got 2 threads reading the same variable and they want to write to it, say you're doing a sum, you can have a thread read the value, second thread reading that same value, and then they both write, +1 to that same variable. If you're doing this in series, you just got, okay, I've got my first value and I add 1 and I add 1. So, you've got original value +2. But because these threads are running in separate processes, they could, they can read the same initial value at 1 and then add 1 to the original value and end up with, original value +1, which I realize is a lot of words. But yeah, I hope that makes sense. If we illustrate this in some code, so I've got basically the same x plus y loop, except instead of saying y equals ax plus y, I'm storing ax plus y in a temporary variable and then storing it in y. So on this side, I'm declaring my temp variable inside my loop, inside my parallel region. So that's fine. Every thread gets its own version of this temporary variable, and it will run just fine. on this side, because I'm declaring my temporary variable before my parallel loop, sorry, for my parallel region, when I read or write this variable here, it's the exact same position in memory. So when I write to this temp variable on thread 1, and then read it back here, there's no guarantee that another thread has written a different value to this temp variable. And your results can be basically undefined.
Is that going to throw an error? Or is it just going to overwrite?
That's just going to run. But there's a way to deal with it. So yeah, so in this case, to fix this, I would have to explicitly tell, okay, I want this temp variable to be private. Everyone gets their own copy. And it works. Yes. Yes. It might have. Is this going to help to draw something? So if let's see if this works. I've got, this is my memory. I'm saying, okay, this is tiny, sorry. This is my memory, and I've got an element named, TMP, my temporary variable is in here. If I'm running a serial code and running one thread at a time, if I'm going through this loop to output this value, I'm going to I'm going to draw this. Yeah, so I'll just draw a thread here, and I'm going to say, okay, I'm going to read this tiny, read this value. I'm going to write to it. I'm going to read from it. I'm going to write to this. Yeah. So this is like if we're not thinking about OpenMP for a while, I'm just doing a loop on a serial code. Yeah? Then if I remove this, I have a second thread that's going to read, then write, then read, then write. So it's like, what we'd like to have is, okay, for this is read and it's write. That's like our first operation. And then this thread might do a read and a write as second operation. This third operation, and this read and write as a fourth operation. But we can't guarantee that if they're writing this, like reading and writing from the same element, then this read might happen first. This read might happen second. This write might happen third, and this write might happen fourth. So if I'm adding 1 to an element every time, I'm reading 0. I'm reading 0 again. I'm writing 1. At this point, I'm writing 1 again, but I'm adding 1 to 1, right? So I'm expected to have read 1, written 2. Does that make sense? Yeah. So there's like the default data sharing properties in OpenMP. So if I declare a variable inside this parallel region, that means every thread gets its own copy. If I do it, so don't specify anything, if I declare my temporary variable here, it's going to be shared by every thread. So that's when you get that problem. Unless I explicitly say, I want it to be private, then they all get their own copy. Okay.
Is there another variable called text? So is that first line indexed? So what happens to that first line in that case?
Here?
Yeah. Do you just kind of like ignore that first line?
Yeah, so I mean, at this point, I mean, you don't ignore it because you have to declare your variable somewhere in your code, right?
After the loop, it should still have the same content that it had at the beginning.
Sorry, I didn't catch it.
After the loop happens, it still has the content in it before the loop starts.
I think in this case, it's undefined what the variable is.
You repeat the question.
Yeah, sorry. So the question was if this TMP variable has the same origin value once you exit this parallel region. And also answer is like, I'm not exactly sure. I think it's not. It does, okay. Then in C, I'm expecting to be the same, but yeah.
To answer the question that you asked, it creates a copy.
Yeah.
If you've got two threads.
It creates, sorry.
Yeah, so in that case, it creates a second copy. Like, so when you enter the loop, because he's declared it private,
It creates an extra
you've
variable.
got one per each thread.
It's not a copy because it's
No,
private,
sorry.
so it has
But
got the
as in
same value.
it copies it to a separate memory location.
Yeah, it
So
creates
it's-
it creates extra variable.
Yeah.
Yeah.
But you'll never see that. You like explicitly, you won't see temp 1, temp 2, temp 3, temp 4, but it does that for you.
Sure.
So if they create a copy of the temp variable, how do they differ from the person?
Creates one copy of the thread.
I mean,
It
effectively,
creates one copy
at
per
this point,
thread.
this is effectively, equivalent right now. Thing is, this is like a small code snippet, but you might have a large piece of code where it makes sense to declare this variable, or it might be coding style that you prefer. But yeah, these two, as they are equivalent. It's just a different approach.
What if you want to modify them in place? Like you want to accumulate the result into.
You can use a reduction clause, which we'll get to in a moment. Yeah, so if you want to, say do a sum over a variable that's shared between them, there's a mechanism called reduction clause. Yeah, which we'll get to in just a sec. Just to finish up the data sharing bit. So mentioned you can specify whether things are shared or private. You can also add a default clause and say, okay, I want all variables that are used in this clause to be either shared or private, or first private or none. None means, okay, the compiler is not going to make any assumptions about the sharing properties of variables, and you have to explicitly specify for every variable in your parallel region. And I'm just going to say it's a bit fiddly to write it all down, but it's very good to use this. Really, I'm saying this twice, use default none. It's a bit annoying, but it's going to save you a lot of bugs by just bringing a little bit of extra effort and explicitly specifying the sharing properties for all variables. If you just say default none, then your compiler will tell you, look, if you forget to specify one, the compiler will tell you, look, this variable x hasn't got its sharing properties declared. Do it. And now to get to Chan's question. So what if I want to, use a variable throughout my parallel loop? For example, if I want to do a sum of elements, you can use a reduction clause. So say OP parallel do, and then reduction, and then the type of reduction you want to do. So in this case, I'm doing a plus for a sum. Minus, you can do max and min for maximum and minimum. And then the variable or variables you want to do that reduction operation over. So in this case, we're summing value of I from 1 through 10 into sum. So if I run this code, what's the result going to be? Yep, 55. If I don't specify the reduction clause, what's the result going to be? Undefined, correct. Because the threads are going to run in whatever order they like. There's no ordering to the way threads run. So it could be 1, it could be 10, it could be 11, any combination of, some like sums of values in this loop. It would be a number, yes. Why we think it would not be a number?
No, that was undefined.
Oh, sorry. Undetermined would be a better word there, yeah. It's undetermined what the result would be. It's definitely defined. Sum is always being written to in every iteration, so it's going to be some number.
You have to define the type of sum.
Yes, you have to define the type. It's like it has to be C or Fortran compliant. So in this case, sum is going to be defined somewhere up here. Yes.
So how do you know how many threads do you create? It just said, do we have to determine it somehow, or is it automatically determine how many threads are available to run?
There are some API calls, there are some environment variables you can set like at runtime before you start program. By default, it will often use just all cores you have available. I think on our cluster by default it's 1, so we explicitly have to set it and make sure that we set it to more than 1, because otherwise we're doing multi-threading with 1 thread. Good luck finding your bugs if you're doing that. Right, so that's really all you need to know about getting going with OpenMP on CPU. But once you learn how to do is use OpenMP to use our GPUs. Am I doing for time? Slightly slow. So a little bit of terminology. So far I've been running code on the CPU. Since the code is running on the host or host device. Sorry, not host device, just the host. But what to do is run a code on a GPU. So in OpenMP parlance, it's called offloading a computation to a device. So offloading is concept of taking a calculation and moving it to basically any external device. In our case, it's a GPU, could be an FPGA, could be some new hardware that no one has developed just yet. And so the instruction we have to give to OpenMP is to tell it to target a device for computation. So using a target directive. And because I'm definitely going to say this offload call, basically it's like call it a kernel or a GPU kernel, a device kernel. So if we go back to our SAXP loop, this is our CPU parallel loop. If I want to run this on a GPU, all I have to do is, add the target keyword. And I can tell you that this works. Excellent, go home. Except this is going to be horrifically slow, because of course there's no free lunch. And to explain why this is slow, I'm going to take a tiny little detour into GPU architectures. Because GPUs have quite a different architecture to CPUs. You could say fundamentally different in some aspects. And this my favorite bad analogy is a CPU can be seen as, say, a bunch of trucks on a motorway, whereas GPU is more of a container ship. Like they can both carry, carry cargo, carry data, but trucks are relatively agile. They can take, any exit they want on the motorway. They can speed up, can overtake. Whereas if you are a container on a ship, well, you're going to where the ship's going. and you're moving a lot of cargo, a lot of data at the same time. So overall, if I'm sending my ship across the sea, I'm getting computation on this whole bunch of data done quite a lot faster. But if I have to do a lot of diverging tasks, my trucks might be better. And so please don't think too much of this. This is what, in this case, an Intel GPU looks like these days. What I really want to see is we've got a bunch of compute tiles that are repeating. So we've got multiple copies of these compute tiles. And then, again, please don't look at the details. But if we look inside these compute tiles, we've got this hierarchy of repeating. So we've got execution units, they've got a bunch of math, they've got vector units. So we've got the key takeaway, we've got a hierarchical architecture of repeating compute units. And OpenMP maps quite closely to this model, or at least OpenMP offloading does. And so if we really want to use our GPU effectively, we have to be quite explicit about how it's going to use all these levels of parallelism. And so we've seen some nice, simple directives. It's a bit less elegant when we're running on a GPU. So we get our favorite OP target teams distribute parallel do SIMD to do the same loop efficiently on a GPU. So this is a bit much to take in, so let's go through this, step by step, break it down a little bit. So if we just look at our target directive, we're just saying, okay, I'm going to take this code and I want to run it on my GPU. So in this case, I'm going to take this loop. I'm saying, okay, I'm saying target, so generate some code that runs on my GPU. Let's work. But I'm only telling it to run on a GPU, so this is going to be serial. And it's only going to run on one execution unit. Sorry. So that is run on GPU. So I can say my parallel do, same as on the CPU. This does my, it distributes the work of my loop. But that is going to run on a small subset of my GPU, running on all the threads in that small unit. I've got tens or hundreds of these units on my GPU. So that's where the teams keyword comes in. This means create a team of main threads, and it's going to create some threads on every execution unit. And I've got this loop running in parallel on an execution unit, and then that same loop on the same data running parallel on the next execution unit. Which is why I need this distribute keyword. This again takes, okay, why am I doing the same computation as every execution unit? Distribute my work. And finally, SIMD is one extra keyword that's used by some vendors and some GPUs. So, okay, use the last little bit of vector parallelism in in the cores themselves. This is a lot to take in, and I'm not expecting you to remember this right now. So, really, the only way to learn this is to do it, which is why I've got the exercise in a bit. For now, just accept it. But it's honestly, it's one of the methods to do it, but it's probably the oldest supported way of doing this, and it's what you probably see most in literature. But it's a very prescriptive way of declaring your parallelism. So it's very verbose. It takes a lot of typing, a lot of effort. But it's also quite powerful because it lets you decide precisely how you want to have your work done. We've been looking at simple single-level loops, but you might have more complex constructs where you might just have that bit of control. There is another way to do this, however. So it's quite recent introduction to standard, which is the loop directive. So this is a descriptive way of parallelizing your loop. In this case, we're just saying OpenMP target, like we did, target device, create teams of threads. But inside these threads, we're saying loop, which is saying a loop directive. And this basically telling compiler, okay, compiler, go nuts, compile this code for me. Sorry, parallelize this code for me. So it's much less verbose. It's easier in a way. But yeah, it's not quite as powerful. And just because, like I said, you see a lot of literature with the more prescriptive way, I recommend getting familiar with it. But in the examples I'll come, I'll probably use loop because it's just a bit more, it's easier on the eyes and doesn't fill up my slides. So that's computation. But there's another thing we have to keep in mind with computation on the GPU, and that's memory. So if we look at my beautiful node diagram for a second, now I've been drawing the CPU and the RAM, but my GPU with its own memory. And so in most GPU devices you see these days, most computers, you'll see that your CPU and GPU have physically separated memory spaces. And definitely in the OpenMP memory model, it's regarded as the memory that's on your host and the memory that's on your device, your GPU, are separate. So there's some data management and data movement involved. And so by default, OpenMP will analyze the loops that you're offloading to your GPU. Just go, okay, I'm going to copy all the data you're using in this loop to the GPU when you're launching this compute kernel. I'll do my work and I'm going to copy everything back. Which is great because it works, but it is, or it can be, or usually is, extremely inefficient. Because data movement is very costly. Like moving data around is a lot slower than actual computation. And you really want to avoid unnecessary data movement. Because if you're running a bunch of compute kernels and you're moving all your data back and forth all the time, you're not going to get a speed up. You'll be lucky if you don't get a slowdown. So yes, there's a bunch of ways to optimize this. And the key actually is the map clause. So now it's mapped. So the OpenMP runtime keeps a mapping between what data you have on your host and CPU and what data you have on your GPU. And there's like your GPU memory almost always have a equivalent on the host. Sorry. So yeah. Like I said, so the map clause provides compiler with instructions to how data should be moved around. So this kind of cryptic way of writing out the format is saying, okay, because map keyword, and then in brackets say the type of operation. So what do we want to do with its memory, and then which variables does it apply to? So the operations are to, from, and alloc. So this is basically seen from the perspective of the host. So to means copy data to the GPU, but don't copy it back when you're done. From's the other way around. It will allocate some data on the GPU and copy the result back, but it's not initially copying the data in. To from is default, it just means copy back and forth. And alloc means allocate some data, but don't do any data movements. So you might use this if you've got a temporary array or temporary variable. And so you can control this data movement either per compute kernel, or you can create data regions if you want to move data, keep data resident across multiple kernels. Yes, question?
So once GPU, is it staying there? You copying data to the GPU, it stays there, and you copy back. That's why you use this from command, or is it?
So depends on that. So if you're doing it per kernel, it will only be resident for the duration of that compute kernel. So if you're saying move to for compute kernel, it will copy it in until the end of your compute, and then it will just delete it. If you start playing around with data regions, you got more control, and you can start thinking about actually keeping stuff resident. So I've got a simple loop here, just taking A and B, summing them, and storing them in C. And so, as I've been saying, by default, we'll be copying A, B, and C to the device as soon as we hit this offload directive. And once you hit the end, we're just going to copy everything back. But let's take a look, how we're actually using this data. Yeah.
So here we are not changing A and B. So does OpenMP recognize that A and B were not muted? So we don't need to move them back.
No, because like by default, it's just like it's not going to make any assumptions here by default. It's just going to copy everything over, copy everything back. And if you want to change, that's like on you as a programmer. So in this case, like you said, we're not changing A and B, we're just reading the values. And C is the other way around. We are writing to every element, but we're not reading what's in there. So in this case, we can use a Makefiles to say, okay, so we're only reading from A and B, so we have to copy them in, but we don't have to copy them back. So we can map them with a to clause. And C is the other way around. We need the final result, but we don't care about the initial values. So we map it with a from clause. And you can see I'm specifying the array range. It's generally advised to just use this either to specify the entire range. You can specify a partial array. You can just specify the name of a variable, and the compiler will do its best to determine the size, but it's not guaranteed. But yeah, in this case, we just cut out half for data movement.
So
yeah,
the initialize what it is outside of the loop, or is it initially copied over?
It's not initialized. It's just allocates some data on the GPU. So that's why keyword here is we're writing to every value of C, or at least every value of C that we're moving. If you only write to parts of C and you're copying everything back, then your end result has a bunch of uninitialized gaps.
C on the GPU get its type.
Type. I mean, that's just inferred from how it's declared on the host side. Every variable on the CPU and GPU, it's a one-to-one mapping. Right. So that's optimizing your movement per kernel, but as someone already mentioned, sometimes you want to keep data resident on your GPU. For example, if you're using it through multiple kernels. So we like to, not have to move the same data around every time for every kernel. And that's where data regions come in. So if you have a data region, you map your data to the GPU and you're going to keep it there until that data region ends. And these regions can either be structured or unstructured. So a structured data region is a scope region. And we use the OpenMP targeted data directive. So in this case, we can call a loop. In this case, we're reading A and B, and we're storing it in B. So we declare data region by saying OpenMP target data, and then a map clause. Exactly the same as when we do it per kernel. But in this case, once we hit this this offload kernel, the runs will now. Okay, I know that these arrays, these variables are already mapped to the GPU, so I'm not going to do any movement of my own. And only when it hits this end target data, like end of the directive, your data will either be copied out if it's mapped from or to from, or it's going to be deleted from the GPU.
We don't have like the extension because of the teams directive and that kind of thing.
There's no race condition here because all these operations are independent. Yes.
Can you have more of this inner loops, this inner blocks, the view of these blocks before this?
For the under yes, you can have any number of offload kernels here.
The target has that the data is moved from CPU to GPU, and with this finally I get all back. Inside I can do what I want.
Yes.
Can you summarize the question?
So in between, like the start of your target data and your end target data directives, any array you specify in these map clauses it's going to be resident on the GPU. So you can do whatever you want with it. Something to keep in mind is that you still have your copy in the CPU. So that's something you have to be careful with. So you can have any number of offload kernels in here. It's just you can only fit so many on my screen. Yeah. So you've got this data tree. So your data is now resident on the GPU, and in general, you really want to keep your data resident most of the time. But sometimes you still have to do some operation on the data on the host side. It might be some input data you're reading that you're reading on the host and have to copy over. There's a couple of ways you can do this. You can nest data regions, so have your main data resident all the time, and then have smaller sections where you have data only rest for a part of the time. Or you can use the update directive. So if I've got two kernels here. Again, I'm reading A and B and writing to B, and then doing something in the second loop. But at this point, I've got my data region all the way from start to the end. But at some point in my code, I'm going out to a function or doing some work that writes to A on the host side. Question?
So, like between these two loops, we are like updating the CPU and like bringing it back to GPU.
Yeah.
So, like would the GPU or like processes on GPU, would they wait until this updation or like updates on A are happening, or would it just like go forward?
That's a very good question I haven't touched on. So the question is, if I'm doing work on these loops on the GPU, and I'm then doing some work on the CPU, will the GPU kernels wait? They will wait because by default, offload kernels are synchronous, which means that once you reach the end of your offload kernel, like the host will wait for this kernel to complete or continue. So your CPU threads will not do anything until this work on the GPU is done.
What about the beginning of the next loop?
So again, at this point, the CPU work, once I reach the end of my this kernel, like the GPU is not doing any work here. And this point, I'm just having some work done on CPU, so no GPU work being done at all. And only once I, have to update directives to move the data back to GPU and then hit my next offload kernel, that's when the GPU starts doing work again. It will just wait.
Out of interest, when you do the update, is that going to reuse the same A variable on the GPU, or is it going to reallocate more space and then basically forget about the A that it had before?
That is a good question. I don't know if that's defined, but for all intents and purposes, it's the same. Okay.
If you have like a massive array or like a really large vector, I guess you'd rather use the same space again rather than
Yeah.
potentially reallocate
I mean, yes,
it.
it will use the same data because you could update a partial array. So we'll write the same data there.
Related to that, like so if you wanted to update partial and say you wanted to update from the middle of A to the end, can you like programmatically put in, instead of 1, you can put in the result of some computation that returns some integer, essentially? Like the question is really like, is the stuff there still responding to the defined integer variables elsewhere in the code? I mean,
Yes.
it looks like it does because of the capital N, but
yeah, that should be fine.
yeah, but you can't do operations. You can't do like 1 plus j or something in that.
Yeah, you can do that. You can do 1 plus j or any valid calculation in there.
It might be only tangentially related. Can I do like nested operation with OpenMP, like nested loop, like those kind of? Do I have to define the directive for each of the nested one, or is it just top level?
You can do nested loops. Yes. So if they are tightly nested, there's something called a collapse clause where you can say, okay, I've got 3 levels of loops that are tightly nested. You can say collapse 3, and it will spread the load over all the GPU cores. If it's a more complicated loop, I'm not really touching on it because it gets more complicated, but especially if you do like your prescriptive, target themes distribute probably do. That's is a compound directive, so you can split that up over multiple levels of your loops and like orchestrate your parallelism that way. But it's a bit more advanced. So question back, yeah?
Yeah, I just missed the answer to the previous question. You can put variable statements in the directive comments, and it will be fine with that. Okay.
Should be fine.
Cool. Thank you.
Any more questions? Yes, Jen. Mike's coming your way.
So can you fuse these loops together into a single loop?
These 2 loops?
Yeah.
Not in this case, because A is going to change in between them. So there's a data dependency on A here.
Okay. So A is copied from CPU to GPU and forward and backward.
So in this case, we've got A is copied to the GPU at the start of this data region, mapping A2. But then at this point, when we have this call CPU work function or routine, A is still resident on the GPU, but we're doing this work on the CPU side. So that's why we've got this update statement to update the GPU copy.
Okay, thank you.
So that's in between like the start and end of this target region, there's no point where A is not resident on the GPU. It's just as soon as we call this routine, it gets outdated and we need to update it. Another question? Yes?
Yeah, sorry, I'm going to hammer on that point again. How aggressive can I get with the statements in the directive? Can I like do full subroutines in the, like, is that just calling another sort of Fortran instance in the statement? So if I wanted to build a subroutine that made some definition and stick it into that end bit.
This is where my knowledge of the spec isn't entirely complete.
Okay.
I think you probably can. The question is, should you?
Yeah. Because it seems like you could do everything there, and then
I mean, it's C or Fortran, right? It's like you can do anything you want.
Okay.
The key is knowing what you shouldn't do. Chris?
The answer is it's what's defined in the spec. The spec says it's scalar expression.
I mean, if your subroutine returns a scalar, that's fine, yeah. I mean, this is probably going to end up in some C or Fortran-style code.
So is it correct in my interpretation then that it is not possible to have CPU and GPUs computing at the same time, and the CPUs will always be waiting for the GPUs?
You can have them overlap. You have to do it explicitly. So there's an async keyword. If I say, well, can we move these? OpenMP target teams loop async. This one asynchronously, and so the CPU thread will just keep running. But at that point, you'll be responsible for make sure your code and your data are synchronized correctly. But yeah, out of scope of this tutorial. Cool. Okay, so that's structured regions. So structured regions or structured data regions are very powerful, but they might not always fit your program. So the alternative is the unstructured data region. In this case, instead of having a target data and target end data directive, we have a target enter data and target exit data directive. And they use, except most of the same map clauses, except enter data will only accept to an alloc, and the exit data will accept, from and then delete or release. Where I'm trying to realize, delete and release are almost equivalent. One of them is based. You can have the same array of. So the same variable show up in multiple map clauses and run just some kind of reference counting, and I think release will say, okay, I don't care how many references you got, just delete this from the GPU. And also important, to from is not accepted as a map clause because it will not make sense in this context. Because, let's see, there we go. If we hit a enter data directive, any data, that just means, okay, I'm mapping this data to the device. It's just going to be resident. It's going to be on the device until I explicitly call a target extra data and I'm on that variable. So in this slightly contrived example, I could have a routine that maps A to the device, call out to a function that does some work on the GPU and copies in the temporary array. I might do some other work elsewhere in the code. And then finally, I hit a point, okay, I'm done with my GPU, I'm getting rid of data. I can have in a completely unrelated location, I can have this exit data statement and then map my A back to my device and delete my temporary variable. Yes.
Are there restrictions on what type of data I can move to the GPU? Stuff like with pointers inside, like can I move it on GPU? Would everything be recursively copied over, or how does it work?
Good question. So if in the OpenMP spec, if you have a C-style struct or Fortran derived type, and you've got allocatable arrays or malloc members, OpenMP will do a deep copy, so it will copy all allocated variables and do like the pointer remapping for you, which is different from OpenACC by default, which does not do it. So yeah, that's something. Yeah, if you copy over a derived type or a struct, it should just copy all its members, and any valid type in the language can be copied over.
Yeah, I was wondering what the ampersand on the end of the penultimate line does.
It's a Fortran line continuation. So it's basically treating these two lines as one line. Like,
Oh, okay, so it's target exit data map data map twice effectively. Yeah.
yes.
Okay.
Yeah. Okay. So since we're running a bit of my plan time anyway, getting close to the end here, that is most of what you need to know to get started with the exercise and get started with, offloading your loops to GPU. There's a few things I want to mention that are interesting, but not very relevant to the exercises. It's exercise left to the reader. There's some additional directives called the declare target directive, which is quite powerful. It declares that something should be present on your GPU for the duration of a program. And something can be quite a lot. So you could use this for variables. Say you've got a global variable that you use throughout your code. So when you declare the variable, you say OMP declare target, and we'll make sure that memory is allocated for the variable. The other very powerful thing is you can use it to generate offload versions of subroutines or functions in C. So if you want to, if you've got a bit more complex code, you want to call out to a function or subroutine inside an offload region, you have to make sure that you mark that subroutine with OMP declare targets. And a few final things. So we've touched on this a bit. So all that we use in these slides and these examples have completely independent iterations. So they are massively parallel. They have no interdependencies between data points. This is pretty much a requirement to efficiently offload your kernels because, if you've got data dependencies between your elements, you're going to run into race conditions. So if you've got a code that does have loops with lots of dependencies, it doesn't disqualify them from offloading, but you may have to do some re-architecting. And a thing which, if you start thinking more about performance, your GPUs like to be overloaded with work. They're very eager little machines. So it's very much the opposite of a CPU. If you've got a CPU with 20 cores, you don't want to run with more than 20 threads, or it will start switching context and thrashing its caches, and it will slow you down significantly. GPUs are built specifically to do a lot of context switching because their memory is a bit slower in latency. So a GPU have probably thousands of cores or compute units. And if you want to efficiently use it, you're going to have to provide with many times as much work. You want to get 10,000s or hundreds of thousands of threads running on your GPU to really efficiently use them. So yeah, that should hopefully be enough to get you started with OpenMP, or at least today's exercises. There's a lot more features. There's task parallelism. Just with a question, you can do asynchronous uploading, which brings the need for synchronization at the end. And as a rule, one thing to keep in mind is any feature that is supported on the CPU side in OpenMP is supported on the GPU side. So, any more final questions? Yes.
Sorry. Lots of questions.
Questions are good.
Okay.
Means you're participating.
This is good. Okay. So if you're in like C++,
yeah,
and you have like a class, can you copy arbitrary classes over to GPUs? I presume there are limitations on what you can copy over.
Do we have any C++ experts in the room? I don't know off the top of my head. I'm not much of a C++ programmer. I'm C or plain C or Fortran.
You would probably offload Typically, I imagine you would probably offload the relevant parts of the computation, like as in, so if your class contains some arrays, you would probably just offload you wouldn't offload the whole class. You'd probably only offload the like actual arrays.
Yeah.
Like kind of because a class will have, in memory will have lots of like metadata which you don't need on the GPU. You only care about the big array that you want to do computations on. So that's typically how I imagine you'd handle that case.
So I guess OpenMP is not smart enough to like do that extraction in of itself and like reconstruct. Yeah, that was maybe a silly question, but yeah.
No silly questions.
No silly questions.
In which case, I can ask a question. I was just curious about race conditions. So in terms of like moving the data across, are we thinking about does the data have to be a kind of unit of like what's the smallest object? I'm thinking in terms of like if you have like an array, is it easy to ship out like parts of the array for like I'm thinking about construction of a large matrix or something? Because I think sometimes I've hit things which feel like they might be race conditions when you're just exporting like rows individually and things like this, which you think would be separate, but I think sometimes, the entire array is considered like the unit rather than a row or something like this. Or maybe that's not.
Chris has got an answer.
Well, I've got an answer. I don't know whether it's the answer to the question. But when Arjen on the slides had the data directives in bracket 1:n, it doesn't have to be 1. It can be 100 to 200, where your array might be 1 to 1,000,000. So you can absolutely move just small chunks of an array.
Yeah. And so, like I said, like all operations in opening offloading are by default synchronous. So if you have to do like chunk movement of data, there's not going to be any places in there.
Is there a way to add thread lock in the parallel loop?
Sorry, can you repeat?
Thread lock, so to prevent like race condition.
Yes.
Yes.
It says yes.
Yeah.
At least there is in the CPU.
Yes. So there are locking mechanisms in.
Thank you.
So you can serialize access to a variable, or you can go with called critical regions.
Yeah, there's atomic.
Atomic. Yeah.
There's critical regions. There's all these different things. You can read the spec.
You can read spec. I wouldn't recommend reading spec. Read the examples document. Yeah.
So Miriam references the syntax reference guide. I'll drop a link in the chat in a second.
Yeah.
I was going to drop a link there earlier, and I looked at it. I thought, no, that's just too overwhelming. It's 16. Because it used to be smaller, the cheat sheet, and now it's 16 pages long.
Yeah.
But yeah.
So there's a very good, I think, programming examples document for OpenMP that for some reason is very hard to find through Google. Because I've been dealing with like trying to read the spec when I couldn't find something for agents. Suddenly this thing start popping up on Google that actually says this is how it's done, not this is how a compiler writes should implement this. Yes.
Is it possible to compile a program that can use OpenMP directives for both CPUs and GPUs? And is there a reason that you might prioritize one type of parallelization over the other?
Yes, and yes. So you can generate code that. So your CPU is a valid target. So you can write code using like the offload syntax and then run it on the CPU. So you don't have to basically like, if you want to run the same loop on the CPU or GPU in different contexts, you don't have to duplicate the code there. And so the second question was, is there a reason to run on one or the other?
Yeah.
Yes, so if you've got a bit of code that's, highly divergent, there's a lot of branches and a lot of, if-else statements, that might not be as suitable for your GPU as GPU. Going back to the container ship analogy, if you're running on a GPU like most threads will run in lockstep, so will run the same computation on different data. So if you've got highly divergent code, it's going to have to like redundant operation, and it will slow your code down quite significantly. If you're doing a lot of random memory access for the same reason, might be better suited for the CPU.
Thank you.
Yeah, I might add to that as well. Like if the thing that you want to parallelize isn't big enough to warrant the data copy transfer, so obviously you pay a penalty for copying data, and it might just be like something smallish, but you still want to parallelize it to like really squeeze that juice out. You can do that. And also you may have like a library function that's not GPU-ified or GPU ready. So you might want to take advantage of thread parallelism. And third option is if you get to the jazzy side of asynchronous stuff and you don't want you want to use your CPU as well and not just leave it sitting idle, you might be able to find some bits of the code, or even you port 90% of it to GPU, like your problem, and then 10% of it you let run on the CPU to really like burn everything and squeeze maximum performance. But yeah, those are some reasons you might do it.
Yeah. So just quickly about what you said about data. So I wanted to include a screenshot of a profile. I didn't get around to it, but I've been working on code. So I'm just going to draw this where I like a timeline profile of my code. So if you've got a timeline, you've got this block, which says like, say, a memory copy, and then another memory copy. It's like, why is doing like a memory copy into the GPU and then out of the GPU? But it has to zoom in my timeline to this bit, and you've got basically the same thing. You've got like a few milliseconds of actually, compute happening here on this line, and so doing 100 milliseconds of memory copy on both ends, just to illustrate how expensive moving data around is. So, about my question.
Yeah. Can you have a GPU parallelized loop within a CPU parallelized loop?
I think technically you can. You might use this if you've got multiple GPUs. You might have a thread per GPU and have them all fire off like an offload kernel to one of the GPUs each. So I don't think there's anything stopping you to do that.
Thanks.
But I think I wouldn't use it for any other reason than that specific use case. I think, are we getting close to coffee, Chris?
It's 5 minutes to coffee, but I think we went upstairs, we could mill around until coffee appeared.
Yeah, I was thinking, like, do you want to spend the 5 minutes to try and get logged in, or do we just go for coffee and then?
I think let's try. So the people who've already managed to log into CSD3, you can go to coffee now, if you're excused. People who haven't